selecting and creating the input descriptors for machine learning. Let's just jump into an example. This is TensorFlow Playground, where you can, from a web browser, just construct and train a neural network. We're going to select different features though. So this is just X1, and if we train just based on this, we can see that we aren't able to predict the orange dots. We overpredict the blue. But if we add this horizontal feature and retrain it again, we can see that the combination of those two is able to distinguish between the blue dots and the orange dots. So our model is the continuous gradient, and the data are these individual data points. You can see the strength of the connection, the weights for the neural network here. Now I could add, for example, another feature that's the product of the two, and then train it again. And you can see that it still fits well, but you can see that the weights of these are very low, so it didn't contribute very much to the overall prediction. And you can see that it might create some things off in the corners. You say, hey, that's not correct, so you wouldn't want to necessarily include that. Or you can do nonlinear transforms of the data as well. So this one's going to be an x1 squared, or you could have x2 squared as well as part of that. Maybe this gives you a better prediction that gives you a high weight here between these. You can look at the input weights as well. So we want to construct input features. These are the inputs to our classification or regression. In this case, it's classification. We could also do that for regression with similar features that help us distinguish and predict continuous numbers, not just ones and zeros, orange or blue, but also continuous values as well. So we can select different input features that help us predict that. Now, if you look at something else, like here's a number, and so let's draw a number. Okay, here's a 7. Alright, or if we drew something else, like, let me go ahead and erase this one, a different number like 2. Okay, you can see that it predicted that it was a 2. If you come back to each individual layer, then we're going to get back to the individual features, and these are going to be the original number that we drew. Those are the input features. These are the pixels of the image that then went into each layer of this convolutional neural network, and finally to predict that this number is a 2. So in feature engineering, we often have variables that we need to convert through nonlinear transforms, or we have categorical data like string information, and we need to convert that into numeric data so that we can process it with machine learning algorithms like classification or regression. There's 3 primary ways that we're going to review here. This is going to be ordinal encoding, one-hot encoding, and then feature hashing. It's a compromise between those two, or those 3. Compromise between the 2. It's a third one. Alright, and then we'll also look at selection and creation of features through things like selecting the best ones that have the most influence on the outcome. So too many features, as we saw even from that simple example, may cause the classifier regressor to predict poorly, especially in areas where you don't have training data. So we just want the minimum number of features. So let's go ahead and get started with this. We're going to have some just sample data here. Okay, I'm going to use this base URL. And if you'd like to follow along with this as well, just use these, the GitHub notebook or the Jupyter notebook. All of the source code is here on the website as well. I want to just go through this step by step to explain what we're going to be doing. So I'll just have the base URL, and then we'll import. I'm going to import NumPy as NP and import pandas as PD. So these are two packages that we're going to use. And then we want to get our data. I'll do read CSV, and I'll use my base URL plus. This is going to be tclabdata6.txt. All right, and then let's just look at data. Okay, so it's 3,600 rows. I have time, Q1, Q2, T1, and T2. The first thing that we want to do is just create a nonlinear transform of one of these columns. So let's just get the log of the time, for example. We can create a new data column in pandas, and if we just say this is going to be the log of the time, and I can do mp.log and just select the time value. Now you'll see that one of the things that's going to happen is it's going to have a 0 value. If I look at the data, then you can see that just that very first one where time was equal to 0 and it's undefined for the log. Okay, so here I've done a nonlinear transform. I've just generated a new feature, which is the log of the time. There are many other types of nonlinear transforms that you can use, and it depends on what classifier or regressor you're going to use. Some of those are linear regressors or classifiers, and so sometimes that nonlinear transform helps those linear regressors or classifiers to work better. Let's go down and do some more data. We're going to, okay, so you can do statistical transforms on this data as well. So let's say we had the T1 mean value that we want to calculate, and we want to do this rolling window. So for time series data, this might be important as a feature. You want to filter out some of the values. We can use rolling. Okay, and I'll say that my window is equal to 100 values, and I'll have it centered. So it's going to take 50 from before, 50 after, and this is going to be the mean of that. So let's go ahead and just show our data now. Okay, I have T1 mean. The first 50 are going to be NaN. Okay, and if I just do drop Na and do this again, then you can see after 51 I start having non-NaN values, and I've just filtered that out, dropping the NaN. Okay, these are going to be the mean values. So let's just plot that. Let's just look at that one and see what it looks like on a graph. Okay, because these numbers are great, but we want to be able to see. Okay, so I have data, and let me plot T1. Okay, so this is going to be T1 and T1 mean, and we'll plot those. Okay, so you can see this orange line, that's the mean value that took 50 from before and 50 after of these blue, and is a rolling average of the values. Okay, we can also do that with standard deviation, skew, and others. I'm just going to change this one here. I'll just say this is stats, and then we'll just include the stats here for just changing it. And so we can use, for example, the standard deviation. Okay, there's the standard deviation of that signal. We can also look at things like skew or kurtosis or others. Okay, so there's many different types of values that we can include on it. Let's see if we can get subplot. Subplot equals true. I think that's it. Okay, so I've just divided it up into these two. You can see, for example, the skew. You could do standard deviation, kurtosis, median, whatever you wanted in terms of this rolling window of values. So this is particularly valuable to create new features, especially for time series data. Okay, let's go to a next section. What about categorical data? And I'm going to have some new data here where we're going to read in PD read CSV, and we'll have the base plus, and then this is going to be animals. Okay, let me put some quotes around animals. Okay, and then we'll print out. Okay, so this is going to be for some cats and dogs, and if we just had a graphic of those, here are the weights and just ordered. Okay, so the smallest animals are here and the heaviest animals are over here, and then each of them has a color as well. So we're going to use color and weight to try to distinguish if this is a cat or a dog. Now we can't just say, after a certain point, these are all dogs, but because we also have a cat here at the end. So we may want to say, well, we also have a dog down here and a couple small dogs down here. So you can see all of the dogs and the cats that are in this data set. So what we want to do is now use some of these features that are going to be strings. And there are 3 different ways of converting these into numbers that we can use for training something like a classifier. So let's first of all just, we've got our data here, and let me just only display the head of that data so it isn't too long. Okay, so there are the first 4 or 5 values, and we want to first of all do ordinal encoding, and we want to change our output label. So we need to do this encoding both for the input features but also for the output labels as well. And let's just create a new mapping, and I can do that with a dictionary. Alright, here's cat is going to be equal to 0 and dog is going to be equal to 1. And then I can say my new label is going to be equal to data and type. I'm going to take it from the type cat or dog, and then I will replace with this mapping. Okay, and let's look at the data head. Okay, so I've created this new column right here by taking the data type and then replacing according to this mapping that I had with cat and dog. Okay, so that's ordinal encoding. We're also going to do that for the color as well. So let's say we had gray is 0, 1 is white, 2 is orange, 3 is brown. So I'm going to use the pd.factorize. Okay, so let's get the color as a number, and if you do factorize, that's going to be this ordinal encoding. So you can either do the mapping. If it's pretty simple, you can choose them yourself, or you can say I just want the first output of that factorize and then data head. Okay, so it's going to assign a number to each one on these colors. So now we have our output label, we have our C number, and we have our weight, and those are all numeric values. Now, one of the problems with doing this ordinal encoding is that this order of the colors may not give good results for the classifier regressor, because there's no reason why gray should be 0 and white should be 1 in between orange and gray. So sometimes that order causes problems for the classification or regression. And what we want to do instead is do something called one-hot encoding. So let's come down here, and one-hot encoding, especially when there are fewer than about 15 categories. One-hot encoding, it's a good option to transform features into numeric values and avoid problems that we saw with ordinal encoding. So the way you do that is data equals data join, and then I'm going to create a new column that's get dummies, okay, data and color. All right, and then let's look at data head. So it's going to create a series of new columns that are each going to be named by this unique color. So and it's going to have a 1 or a 0 for each one. So brown, those are all zeros. There are other browns in this data set, but gray, you can see that's 1 here and 1 here because that is gray, and here it's gray. So it just created these 1, 2, 3, 4, 5 additional columns, and there's a 1 or a 0 there for each one. So this is called one-hot encoding. But what do you do if there are too many of these different categories? So more than 15, for example. Or this also creates just a number of new features that may not be desirable for our application. So there's a compromise between the two. I think I went back and let me just rerun this. I can only do that once because I transformed it already and it's trying to make a copy of that. So what I'm going to do is just, okay, only run that once. And then insert a cell below. Okay, so let's go on to this feature hashing technique. And I'm going to use from sklearn this feature extraction, and I'll import feature hasher. Okay, this feature hasher is going to be feature hasher, and then I can select the number of features that I want to add. So in the ordinal encoding, I added 1 new feature. With this other method of one-hot encoding, I added 5 new features. But let's say I want to compromise in between and only add 2. So I'll put number of features equals 2, and then input type equals string. Okay, so it knows it's getting an input string, and then I'm going to go ahead and do the fit transform. So this one, similar to how we scale the data, but it's going to do the feature hashing, okay, based on the color, and then I'll put that out to an array. Okay, and then the number of, so let's do this PD. I'm going to, the new columns, the 2 new columns are going to be a new data frame with this HT variable. And then I just need to give the new column names. Okay, I can call this whatever I want. It doesn't really matter. But let's go ahead and just call this column 1 and column 2. Okay, so those are my column names. And then I'm going to join this to my data, okay, with these new columns. And then let's do data head. Okay, so now I have these new columns right here, column 1 and column 2. And so I have values of 0, -1, 2, and it's going to be something similar to what's shown here on the right. If I plotted those, the orange would be up here at y equals 2, for column 2, and then column 1 would be 0. All right, and then my other colors are in this space as well. So it chose these values only expanded it to 2 additional features to convert that color, which 5 different colors, into just 2 individual features by giving it an X and a Y value. Okay, so that is feature hashing. It's a compromise between the 2 methods, the one-hot encoding and the ordinal encoding. Okay, but now we have all of these additional features right here. Maybe we're trying to decide, well, which one is the best to use for my application. And so fortunately, there are some very nice tools that you can use to assist in that. One of them is the select K best within the sklearn. And what we'll do is just go ahead and import this. This one's going to be from sklearn, and do feature selection. We'll import select K best. All right, and then we also want to be able to import how we evaluate which ones are the best. And there are 3 primary ones that we would typically use, 2 for classification and 1 for regression. Here's a chi-squared statistical analysis. There's 3 chi-squared. This is really only for stats of non-negative features. We do have the F regression as well. It's the F value between label feature for regression tasks. And then we also have the ANOVA F value between the label and feature for classification tasks. So really the main thing is you can use this one for non-negative features. You can use this one if it's regression, and then this one if it's classification. Okay, so anyway, those are 3 that I've typically used, but there may be others as well. Okay, so you can use, so for example, chi-squared, and let's go ahead and import matplotlib.pyplot as PLT, and let's see, I want to now get my best features, and we'll say that's select K best, and we'll go with the score function, and that's going to be my chi-squared. All right, and then K equals all. All right, and what I want now is I'm just going to use the features that are positive. Okay, so I'm just going to use the colors and then the C number as well. So let's say I had data.columns. And let me go ahead and just print these out so I can copy them. Okay, I'll just copy these. All right, and these are the features that I want to use and be able to select which ones are going to be the best among these. Okay, so let's just go ahead and say that my X's, my input features, are going to be equal to data of F, and then my Y is going to be data, and then I'm going to use label. Okay, so those are going to be my X and Y values, and then I want to fit and get my best features that I just created with fit and X and Y. Okay, so I'm going to run this. Now it's I can do things with this now that I can get the scores from it. So if I just look at fit, this is going to be scores underscore. Then I can see the scores for each feature. Okay, I can also get, let's just go ahead and plot these though. Let's do PLT bar. Height. Okay, so I need the height. I need the categories. Let's see if this will work. Okay, so this is going to give me, how important each of those features are. And so I can see the C number, brown, gray, orange, tan, and white, although I may not want to use the ordinal encoding, but you can see that white is not very important in terms of distinguishing the animals, okay, between dog and cat. But the other ones are important. C number has a very high one, but there's that order that we don't necessarily want in our predictions. Okay, so that's it for this. We can sort these, for example, maybe just take the highest values to use for classification or regression. All right, a couple other things I wanted to show you are some of these other, the SHAP. This is Shapley Additive Explanations, and this gets into explainable AI. This is a very nice package for feature engineering where it graphically shows you some of the relationships between the features and which ones are going to be most important. Okay, so it shows you which ones have a positive effect or negative effect. It is able to put them kind of in relative importance, show you on these timeline type plots. It also shows a sample order, for example, for time series data, how important different parts of the time series are as well. It can give you as well some other types of analyses on your features. Okay, so here's, for example, a natural language example with transformers and others. Here's one, for example, when we showed the classification with the numbers, what parts of those are the most important. So it can give you a SHAP value for each of those, and not just show you, where the influence is, but which ones are most important for coming up with that digit in terms of the identified digit. Okay, and I can also do that for images as well. So what parts of the images are most important for distinguishing between, animals, for example. And so it can give you the features that it came up with to say, these are the most important pixels that are important to make that classification. All right, so that's a nice package. I haven't actually used it yet, but I've just read a little bit about it, and I encourage you to also, if you find anything out about it, go ahead and put that in the comments. I want to show one other thing as well. Down here, okay, these again are all the, there's feature tools as well that you can use to assist in automating the generation and curation of derived features. And this one's been particularly helpful. So what this one does is it helps you take your original features and then it automates, basically you have maybe these features, and it does things like take the product of those, okay, or maybe it takes the summation, okay, of those, and it creates this whole additional suite of features that are derived from this original set. And then you could use things like select K best to say, okay, that one is the most important, or maybe this one is important, this one's important, and that one's important. So it automates the creation of some of these features, and both for time series but also relational data sets. So it combines these together to find what are the best explanatory variables for this outcome. Okay, so that was the final one, and then there's a few exercises here. This one is feature engineering in terms of being able to predict whether the heater is on or off. And so we took an original temperature and then basically the derivatives, the first derivative and the second derivative, those were also very important to help us determine when the heater was on or off. And so there's a case study there for equipment health, and we could also use that for cybersecurity as well. If we're commanding this heater to be on, but there's someone that's making it turn off or making it behave differently than it should. There's also another exercise here on physical and chemical properties of a lithium-ion silicate cathodes to predict the crystal structure of a lithium-ion battery material. And you want to be able to predict that as monoclinic, orthorhombic, okay, or triclinic. And it shows how feature engineering improves the classification results. So there is this case study. I encourage you to go over this one as well, with original numeric features only, with the ordinal space group, and others. So there's a notebook here that you can use to go through that. Okay, well, I hope you've enjoyed this this journey on feature engineering. We've reviewed nonlinear transforms. We've done some things with encoding types, statistical transforms, encoding types with our categorical data, and then the select k best or other statistical measures to determine which features are most important. And I'm just going to come back here to data engineering just to give an overview of where we are with this. This is feature engineering. It's the first topic of part 2. And if we just come back to our overview flowchart, the feature engineering is right here, where we determine, after we do our data assessment, if we have enough features. And if we don't, then we need to increase the data diversity or select new features that help us to achieve the intended outcome, which is going to be a classification or regression. And then once we do that, we cleanse the data, we scale the data, and then we'll split it into train, validate, and test. And then from there, get our labels, and then do classification, regression, clustering, dimensionality reduction, or other methods with that data.